Have you ever seen a bridge that looks like it's floating in midair? Right now, in Taiwan, engineers are putting the finishing touches on the Danjiang Bridge, a structure so impossibly elegant that it seems to defy the laws of physics itself. This isn't just any bridge, we're looking at a 920-meter engineering marvel that's costing $400 million to build, designed to withstand magnitude 7.0 earthquakes and typhoons winds while serving vehicles, trains, cyclists, and pedestrians simultaneously. But here's what makes it truly extraordinary. It's about to become the world's longest single-tower asymmetric cable-stayed bridge, and its revolutionary design is changing how engineers think about building in earthquake zones forever. So how do you build a bridge that can survive Taiwan's most extreme natural disasters while looking like a work of art? And why has this project taken over 2 decades to complete? Time to find out. To understand why the Danjiang Bridge is such a breakthrough, we need to understand Taiwan's unique geographical challenge and why this particular crossing has been a problem for over 20 years. Taiwan sits directly on the Pacific Ring of Fire, where the Philippine Sea Plate crashes into the Eurasian Plate. This makes it one of the most seismically active places on Earth, experiencing over 18,000 earthquakes annually. The island also faces an average of 4 typhoons each year, with winds that can exceed 250 kilometers per hour. But the Tamsui River crossing in northern Taiwan presented an even bigger challenge. This waterway connects 2 rapidly growing districts, Bali and Tamsui, while serving as a critical gateway to Taiwan Taoyuan International Airport. The existing infrastructure was completely overwhelmed, with the old Taipei Bridge creating massive traffic bottlenecks that could add hours to what should be a simple journey. Here's where it gets complicated. The Tamsui River isn't just any waterway, it's home to some of Taiwan's most sensitive ecosystems, including protected mangroves and wetlands that serve as crucial habitat for migratory birds. Any bridge built here would need to minimize environmental impact while handling enormous traffic loads. For decades, engineers faced an impossible choice: build a traditional multi-tower bridge that would require multiple pillars in the riverbed, destroying the ecosystem, or find a completely new approach that had never been attempted at this scale. The stakes couldn't be higher. This crossing serves as a vital link in northern Taiwan's transportation network, connecting highways with the new Danhai light rail system. A failure here wouldn't just disrupt local traffic, it could cripple access to Taiwan's main international airport and one of Asia's busiest shipping ports. That's when Taiwanese engineers decided to attempt something that had never been done before at this scale. What they're building is pushing the boundaries of bridge engineering further than anyone thought possible. The Danjiang Bridge features the world's longest asymmetric cable-stayed design, with a single 200-meter tower positioned not in the center but deliberately off to one side. At first glance, it looks unbalanced, almost precarious. That's because it is, intentionally. Here's how radical this design is. Traditional cable-stayed bridges use 2 towers for balance and stability. The Danjiang Bridge uses just one. The main span stretches 450 meters west of the tower, while the back span extends only 175 meters east. Conventional engineering terms, this should collapse under its own weight. But here's the genius. The asymmetric design actually makes it more earthquake resistant, not less. During seismic activity, symmetric bridges can develop resonance frequencies that amplify the earthquake's motion. The Danjiang Bridge's intentional imbalance disrupts these frequencies, allowing it to flex and absorb earthquake energy rather than fighting against it. The tower itself is a marvel of engineering precision. Standing 200 meters tall, roughly the height of a 60-story building, it's being constructed in 53 separate sections, each with a different geometric shape. As the tower rises, its cross-section changes from convex at the bottom to concave at the top, creating what engineers call an ever-changing geometry that requires completely different construction techniques at each level. The bridge deck will support multiple transportation modes simultaneously. The top level handles vehicle traffic, while the lower level accommodates the Danhai light rail system. Dedicated lanes for cyclists and pedestrians ensure this isn't just a car bridge, it's a complete transportation solution, but the real innovation lies in the cable system. Unlike symmetric bridges where cables can be installed in balanced pairs, each of the 256 cables on the Danjiang Bridge must be tensioned individually to precise specifications. These cables connect to 128 double rope pulleys and are anchored to 4 massive reinforced concrete towers, each standing 169 meters high. But building this architectural impossibility hasn't been easy. The challenges have been enormous, and they explain why this project has taken over 2 decades to complete. The story begins in 2001 when planners first recognized the need for this crossing, but it wasn't until 2014 that the project received its 12.49 billion new Taiwan dollars budget, approximately 400 million US dollars. Even then, the real work was just beginning. In 2015, an international design competition attracted the world's top architects. The winning design came from Zaha Hadid Architects, led by the late Zaha Hadid herself. Her vision was revolutionary, a single, slender, 200-meter pylon that would minimize visual obstruction of the Tamsui River's famous sunset views while creating a landmark that harmonized with the natural beauty of the area. But turning that vision into reality required solving problems that had never been encountered before. The first major challenge was the foundation. The bridge needed to be anchored in the Tamsui River, where the riverbed consists of soft alluvial soil that shifts constantly. Engineers had to develop new techniques to ensure stability without disrupting the delicate ecosystem. Then came the tower construction, which began in earnest in 2020. Because the tower's geometry changes at every level, engineers from Perry Group had to develop specialized formwork systems that could adapt to each section's unique shape. Traditional construction methods simply wouldn't work. The asymmetric design created another unprecedented challenge. Unlike symmetric bridges where loads are balanced, the Danjiang Bridge experiences constantly changing forces as traffic crosses. Engineers had to develop new computer modeling systems to predict and account for these dynamic loads. Weather added another layer of complexity. Construction has been halted multiple times due to typhoons and severe weather. The partially completed structure has already survived several major storms, proving the design's resilience even before completion. Environmental protection requirements made everything more complicated. Every aspect of construction had to be carefully monitored to ensure minimal impact on the surrounding wetlands and mangroves. This meant using specialized equipment, limiting construction hours, and implementing extensive environmental monitoring systems. The human effort has been staggering. Over 2,000 workers have labored on this project across multiple construction seasons, working in shifts around the clock during suitable weather windows. The project requires 45,000 tons of steel and 180,000 cubic meters of concrete, enough material to build a small city. This level of innovation isn't happening in isolation. Around the world, asymmetric cable-stayed bridges are emerging as solutions to extreme engineering challenges, but none approach the scale and complexity of the Danjiang Bridge. In China, the Sutong Bridge uses asymmetric principles to span the Yangtze River, but with a more conservative design approach. In France, the Pont de Normandie employs similar concepts to handle coastal winds, but in a less seismically active environment. In Japan, several bridges incorporate asymmetric elements for earthquake resistance, but none attempt the extreme span ratios being achieved in Taiwan. The Danjiang Bridge represents the most ambitious application of this technology. While other asymmetric bridges typically maintain span ratios of 2:1 or at most 3:1, the Danjiang Bridge pushes engineering to its theoretical limits. International attention has been intense. Even before completion, engineering delegations from over 20 countries have visited the construction site to study the techniques being developed. The innovations here are already being incorporated into bridge projects in earthquake-prone regions from California to Turkey to New Zealand. The bridge has become a testing ground for next-generation construction technologies. The specialized bearings developed by Magabe Group include innovative fuse elements designed specifically for seismic protection. These bearings can absorb earthquake energy while maintaining structural integrity, technology that's now being adapted for other critical infrastructure projects worldwide. Computer simulation techniques developed for this project have revolutionized how engineers model asymmetric structures. The software created to predict the bridge's behavior under various load conditions is now being used for major infrastructure projects across Asia and beyond. What makes this project truly remarkable is how environmental protection drove engineering innovation rather than constraining it. The single mast design wasn't just an aesthetic choice, it was an environmental necessity. Traditional multi-tower bridges would have required multiple pillars in the riverbed, destroying the very ecosystems the bridge was meant to preserve. By using just one tower, engineers minimized the bridge's footprint while actually improving its structural performance. The Tamsui River estuary is home to protected mangroves and serves as a crucial stopover for migratory birds traveling the East Asian Australasian flyway. Environmental impact studies showed that traditional bridge designs would have disrupted these migration patterns and destroyed critical habitat. The solution required rethinking everything. Computer simulations tested not just structural performance, but also environmental impact. Engineers modeled how the bridge would affect wind patterns, water flow, and even light penetration to ensure minimal ecological disruption. The slender pylon design preserves the area's famous sunset views, a consideration that might seem trivial, but actually reflects a deeper understanding of how infrastructure should integrate with its environment rather than dominate it. This approach has influenced environmental design standards for major infrastructure projects throughout Asia. Construction techniques were adapted to minimize disruption. Work schedules were coordinated with bird migration patterns. Construction noise was limited during sensitive periods, and specialized equipment was used to prevent water contamination. The result is infrastructure that enhances rather than degrades its environment, a model for sustainable development that's being studied and replicated worldwide. So how does this actually work? The key lies in what engineers call controlled asymmetry, deliberately creating imbalance to achieve stability. Think of it like a giant balance scale, but instead of trying to keep both sides equal, engineers deliberately make one side heavier and use that imbalance to create stability. The shorter backspan acts like a massive counterweight, while the longer mainspan distributes load across a wider area. The cable system uses a modified fan arrangement where 256 cables connect to the tower at different heights and angles. This creates what's called a three-dimensional load path. Instead of forces traveling in simple straight lines, they spiral around the tower, distributing stress more evenly throughout the structure. During earthquakes, the bridge doesn't fight the motion, it dances with it. The asymmetric cable arrangement prevents the dangerous resonance frequencies that can tear apart conventional bridges. Instead of rigid resistance, the bridge flexes and absorbs seismic energy. The tower construction represents a masterpiece of precision engineering. Built in 53 sections, each with its own unique geometry, the tower required developing new formwork systems for every level. Perry Group's engineers had to create versatile systems that could adapt to the constantly changing shape while maintaining structural integrity and construction speed. Seismic protection comes from multiple systems working together. Specialized bearings from Magiba Group include fuse elements that can absorb earthquake energy while maintaining structural connection. These bearings represent a breakthrough in seismic engineering, allowing controlled movement while preventing catastrophic failure. The multimodal deck design required solving complex load distribution problems. Vehicle traffic, rail systems, pedestrians, and cyclists all create different load patterns and vibration frequencies. Engineers had to ensure that these different uses wouldn't interfere with each other or compromise structural integrity. As of 2025, the Danjiang Bridge is in its final construction phases, with completion expected in early 2026. The project has progressed steadily despite the enormous technical challenges, with no major delays reported in recent updates. The main tower construction has been completed, representing one of the most complex concrete pours ever attempted. The cable installation is ongoing, with each cable requiring individual tensioning to precise specifications. This process alone takes months, as engineers must ensure perfect balance in the asymmetric system. Recent construction photos show the bridge taking its final form, with the distinctive single tower silhouette now dominating the Tamsui River skyline. The structure has already survived several typhoons during construction, validating the design's resilience even before completion. Final phases include deck completion, rail system installation, and extensive testing of all systems. The multimodal nature of the bridge means that vehicle traffic, light rail, pedestrian, and cycling systems must all be tested and certified before opening. Environmental monitoring continues throughout construction, with regular assessments showing minimal impact on the surrounding ecosystems. The protected mangroves and wetlands remain healthy, proving that major infrastructure can coexist with sensitive environments when properly designed. The project has maintained its budget of 12.49 billion new Taiwan dollars, a remarkable achievement for such a complex and innovative undertaking. This financial discipline, combined with technical success, has made the Danjiang Bridge a model for major infrastructure projects worldwide. The completion of the Danjiang Bridge will represent more than just a transportation link. It's a glimpse into the future of infrastructure in an era of climate change and extreme weather. As extreme weather events become more frequent and intense, the engineering principles proven here become increasingly valuable. The bridge's ability to withstand major typhoons while maintaining normal operations offers a template for climate-resilient infrastructure worldwide. The success of this project has already influenced infrastructure planning across Asia. Taiwan is considering additional asymmetric cable-stayed bridges using lessons learned from the Danjiang project. These future bridges will incorporate even more advanced materials and monitoring systems, building on the innovations developed here. International collaborations are expanding rapidly. Taiwan is sharing its expertise through partnerships with earthquake-prone regions, including California, Chile, and the Mediterranean. The techniques developed for the Danjiang Bridge are being adapted for projects in these regions, helping develop the next generation of disaster-resistant infrastructure. The environmental integration achieved here is setting new standards for sustainable infrastructure development. The principle that environmental protection can drive rather than constrain innovation is being applied to major projects worldwide, from urban development to renewable energy installations. Construction techniques developed for this project are reducing build times and improving safety for similar projects globally. The modular approaches and specialized equipment created for the Danjiang Bridge are now being used on major infrastructure projects across multiple continents. From a 20-year planning process to a global model for disaster-resistant infrastructure, the Danjiang Bridge proves what's possible when innovation meets necessity. This $400 million investment represents far more than a river crossing. It's created a new paradigm for building in extreme environments, demonstrated that environmental protection can drive engineering innovation, and established Taiwan as a world leader in seismic bridge design. The bridge stands as proof that sometimes the most elegant solutions come from embracing imbalance rather than fighting it. In a world facing increasing natural disasters and extreme weather, the lessons learned here offer hope that human ingenuity can create infrastructure that doesn't just survive, but thrives, in harmony with nature's most powerful forces. When the Danjiang Bridge opens in 2026, it will carry more than traffic across the Tamsui River. It will carry the hopes and innovations of engineers worldwide who are working to build a more resilient future. The techniques developed here, the environmental standards established, and the proof that ambitious engineering can coexist with ecological protection will influence infrastructure development for generations to come. As climate change intensifies and urban populations grow, we'll need more infrastructure that can adapt, flex, and endure. The Danjiang Bridge shows us that the future of engineering isn't about building bigger or stronger. It's about building smarter, more sustainably, and in harmony with the natural world. What do you think the next breakthrough in disaster-resistant infrastructure will be? Will we see more single-tower designs pushing even further limits, or perhaps entirely new approaches to building in extreme environments? Let us know your thoughts in the comments below. And if you're fascinated by incredible engineering projects that push the boundaries of what's possible, make sure to check out our other videos exploring the world's most ambitious infrastructure projects. Don't forget to subscribe and hit the notification bell so you never miss our latest deep dives into the engineering marvels shaping our world.